The Big Bang. You've heard of it. Beginning of everything. Time starts. Space starts. Matter appears from nothing. Simple story. Clean. Satisfying. Not approximately wrong. Fundamentally wrong. The Big Bang wasn't the beginning. It couldn't have been. And I'm going to show you why. Not with philosophy, not with metaphors about turtles all the way down, but with actual physics, with measurements, with the same reasoning that tells us what's inside stars we'll never visit and what happened in the first microsecond of cosmic history. Here's the problem. You think beginning is a simple concept. It's not. You think time is something that just exists with a clear starting point. It doesn't work that way. And you think the Big Bang was some kind of explosion in empty space. There was no space, there was no in, there wasn't even a before in the way you're imagining it. So let's start with what you actually mean when you say beginning. You mean a time when nothing existed, then suddenly something did. First frame of the movie. But that's already broken, because when assumes time exists, and nothing assumes space exists to be empty. You're smuggling in the entire framework of reality before you've explained where that framework came from. The Big Bang didn't happen at a point in space, it happened everywhere. All of space was compressed, not into a point in some larger space, but compressed into itself. The entire universe, everything that exists now, was smaller, much smaller. How much smaller? Pick a number, any number. You're wrong. It was smaller than that. Smaller than an atom. Smaller than a proton. Keep going. We can trace it back to sizes so small that our current physics stops making predictions we can test. And here's what nobody tells you. When physicists say the Big Bang, they're not talking about a moment. They're talking about a process, the period when the universe was extremely hot and dense and expanding rapidly. That process, we can see it right now. You want evidence? Look at your TV when it's tuned to static. About 1% of that static is cosmic microwave background radiation, photons that have been traveling for 13.8 billion years, left over from when the universe was 380,000 years old. That's not speculation, that's measurement. We've mapped those photons. We know their temperature, 2.725 Kelvin. We know their spectrum. It's a perfect black body curve, exactly what you'd expect from a universe that was once much hotter and has been cooling ever since. But here's where it gets interesting. That radiation tells us the Big Bang happened. It doesn't tell us the Big Bang was the beginning. Those are different claims, very different. Think about this. The universe is expanding, everything is moving apart. Run that backward in time and everything gets closer together. Keep going back and the universe gets smaller, denser, hotter. Keep going and you reach a point about 13.8 billion years ago where our equations break down. Temperature infinite, density infinite, our physics stops working. That's called a singularity. Now here's the question everyone asks, and almost nobody answers honestly. What happened before that? The standard answer is there was no before. Time itself began at the Big Bang. That's not an answer. That's giving up. Let me be clear. It might be true, but it might not be. And the difference matters. Because when you say time began, you're making a specific claim about the nature of reality. You're saying that the laws of physics themselves came into existence. You're saying there's no causal chain, no mechanism, no deeper explanation. Everything just started. Does that bother you? It should. Every other time in physics when we've hit a wall like this, when our math gives us infinities, when our theories break down, it meant we were missing something. Infinity isn't a feature of reality, it's a red flag. It means your theory has reached its limits. So let's do what physicists actually do. Look at what we measure, see where the theory works, and be honest about where it doesn't. We measure cosmic microwave background radiation, check. We measure the abundance of light elements, hydrogen, helium, lithium, and they match what we'd expect from a hot early universe. Check. We measure the large-scale structure of galaxies, and it matches what we'd expect from tiny quantum fluctuations in the early universe getting stretched out by expansion. Check. But all of these measurements tell us about the universe when it was already expanding, already cooling, already following the rules we know. They don't tell us about the singularity. They can't. Because at the singularity, our theories fail. General relativity, Einstein's theory of gravity, tells us how space and time curve in response to matter and energy. It's incredibly successful. It predicted the bending of light around stars before we observed it. It predicted gravitational waves a century before we detected them. It tells us how the universe expands, but push it too far to the moment of the Big Bang and it gives you infinite density, infinite curvature. That's not a prediction, that's a breakdown. Quantum mechanics tells us how particles behave at small scales. It's even more successful than relativity. Every piece of technology in your pocket depends on it. But quantum mechanics doesn't include gravity. It can't tell you what happens when space itself is quantum mechanical. So we have two theories. Both work perfectly in their domains. Neither works at the Big Bang. That's not a philosophical problem. That's a practical one. We need a theory of quantum gravity. And here's where it gets strange. Every attempt to build a theory of quantum gravity suggests the singularity isn't real. It's an artifact of using the wrong theory. Think about what that means. The beginning might just be where our current understanding ends, not where reality ends, where our equations end. Now, I'm going to tell you about something called inflation. Pay attention because this changes everything. In the 1980s, Alan Guth noticed a problem. The universe is too smooth. Look at the cosmic microwave background from opposite sides of the sky, regions that are 26 billion light years apart now. They have the same temperature. To within 1 part in 100,000, they're identical. But according to standard Big Bang theory, those regions were never in contact. Light from one could never have reached the other. So why are they the same temperature? Things only come to the same temperature if they can exchange heat. If they're causally connected, the answer: inflation. A period of exponentially rapid expansion in the first fraction of a second. We're talking 10 circumflex 36 seconds after whatever you want to call time zero. During inflation, a region smaller than a proton expanded to larger than a grapefruit. Faster than light? Yes, but space itself is expanding, and that's allowed. Special relativity says nothing can move through space faster than light. It says nothing about space itself. Inflation solves the smoothness problem. It solves several other problems, too. And it makes predictions we can test. Those tiny quantum fluctuations I mentioned, inflation stretched them to cosmic scales. We measure their signature in the cosmic microwave background. It matches. But here's what inflation really does. It pushes the beginning further back. The Big Bang, that hot, dense state, wasn't the start. Inflation came first. The Big Bang was what happened when inflation ended, when all that energy driving the expansion got converted into matter and radiation. The Big Bang was the aftermath, not the origin. So what came before inflation? Now we're into territory where we're honest. We don't know. But we have ideas, real ideas, with mathematics, with testable predictions. One possibility: eternal inflation. Inflation, once it starts, creates more space so fast that even though it's ending in some places, creating big bangs like ours, it's continuing elsewhere. Our universe might be one bubble in an eternally inflating multiverse. Time doesn't have a beginning because inflation never started. It's just always been happening. Another possibility: the universe is cyclic. It expands, contracts, bounces, expands again. The Big Bang was a big bounce. What came before? Another universe collapsing. What came before that? We don't know. Maybe it cycles forever. Maybe not. A third possibility: from quantum gravity, time itself is emergent. At the smallest scales, the Planck scale, 10 circumflex 35 meters, space and time might not be continuous. They might be discrete, quantized like energy levels in an atom. At that scale, asking what came before might be like asking what's north of the North Pole. The question doesn't make sense because the framework you're using, continuous time, breaks down. Which of these is right? We don't know. We don't know because we can't test them yet. We don't have the technology to probe energies high enough or times early enough. But here's what we do know: the idea that the Big Bang was the absolute beginning, that time itself started there. That's just one possibility, and it's probably the least likely one. Every time we've thought we hit a fundamental beginning in physics, we've been wrong. Atoms are indivisible. Wrong. They have nuclei and electrons. Nuclei are fundamental. Wrong. They're made of protons and neutrons. Protons and neutrons are fundamental. Wrong. They're made of quarks. We keep finding deeper layers. Why would time be different? Now let me show you why this matters. Why it's not just abstract cosmology with no connection to anything real. The cosmic microwave background isn't uniform. It has tiny variations, hot spots and cold spots. Those variations are the seeds of all structure in the universe. Regions that were slightly denser became galaxies. Regions that were slightly less dense became voids. The pattern of those variations, it matches exactly what you'd expect from quantum fluctuations during inflation, stretched to cosmic size. We measured this precisely. The WMAP satellite, then the Planck satellite, mapped the entire sky. The data matches the predictions from inflation to incredible accuracy. That's not philosophy, that's evidence. But here's the kicker. Those quantum fluctuations mean the universe was fundamentally probabilistic from the start. There's no classical history you can trace back to a single point. Quantum mechanics doesn't give you the universe was exactly like this at time zero. It gives you probabilities. Many possible histories. The universe doesn't have a single past. It has a superposition of pasts that became definite through decoherence as things got bigger and colder. Think about what that means for the question, what came before? Before might not be a single thing. It might be many things, quantum mechanically interfering. Your brain doesn't like this. Your brain evolved to track predators and find food, not to understand the origin of everything. Your intuition says time flows, causes precede effects, everything has a beginning. But that intuition is built from experience in a large, cold, classical universe. It breaks down at the Big Bang the same way your intuition about Newton's laws breaks down at the speed of light. Einstein didn't keep intuition, he replaced it. He built new intuition from the mathematics. And the mathematics of general relativity says time is part of the geometry of space-time, not a background stage. Time can curve, time can slow down, time can end or begin at certain places in space-time, like at a black hole singularity. But just like with the Big Bang singularity, when general relativity predicts a singularity inside a black hole, we think it's wrong. Not wrong about black holes, those are real, we photographed them. Wrong about the infinite density at the center. Quantum effects should prevent that. They should replace the singularity with something else. Something we don't yet understand fully, but that's finite, calculable. The same logic applies to the Big Bang. The singularity is probably not real. Something quantum replaces it, and that something might not have a beginning at all. Here's where we are. We can trace the history of the universe back to 10 circumflex 43 seconds after the conventional Big Bang, the Planck time. We can tell you the temperature, 10 circumflex 32 Kelvin. We can tell you the density, 10 circumflex 96 kilograms per cubic meter. We can describe how quarks formed, how protons formed, how nuclei formed, how atoms formed, how stars formed. All of that is tested, verified, as solid as any science gets. But before the Planck time, that's where we need quantum gravity. And we don't have a complete theory of quantum gravity yet. We have candidates, string theory, loop quantum gravity, others. Each makes different predictions about what replaces the singularity. None has been tested definitively. So when someone asks, what came before the Big Bang? The honest answer is, we don't know, but we have good reasons to think the question makes sense, and better reasons to think the Big Bang wasn't the beginning. That's not satisfying. I know, you want the answer. But physics doesn't give you comfort. It gives you what we can measure and calculate and test. And right now, we can't measure what happened at the Planck scale. We can calculate, make models, see what they predict, but we can't test them yet. Maybe we never will. Maybe the information was erased by inflation, smoothed out by expansion, or maybe we'll find a way. Gravitational waves from the Big Bang, imprinted at the Planck scale, might carry information we can detect. Or maybe quantum gravity makes predictions for things we can test in particle accelerators or in extreme astrophysical environments. But here's what we do know with certainty. The universe had a hot, dense state 13.8 billion years ago. It's been expanding and cooling ever since. That's the Big Bang. That happened, but that hot, dense state came from somewhere. It had a cause, or a precursor, or a quantum origin, something. And that something is not nothing. Return to where we started. You thought the Big Bang was the beginning. You thought time started there. You thought asking what came before was meaningless. Now you know better. The Big Bang wasn't the beginning. It was a transition. From what to what, we're not sure yet. But every measurement we make, every piece of evidence we gather, points to something more fundamental beneath it. The universe you live in is stranger than you imagined. Not mystically strange, physically strange, strange in ways we can describe with mathematics and test with experiments. Strange in ways that have consequences for what exists and how it got here. And we're not done figuring it out. Maybe we never will be. Every answer leads to deeper questions. That's not a bug. That's the whole point.